Welcome to molar volume of a gas. Also in this particular video, we will be doing conversions between moles and liters. 1 mole of any gas at STP, remember STP means standard temperature and pressure. These values can be found on table A on the front of your reference table. And these values just kind of mean a set of conditions. So any gas that we put at these particular conditions, 0 degrees Celsius, 101.3 kPa, will occupy 22.4 liters of space, which is a little bit bigger than a basketball, so it's actually kind of a lot of space. So I put a figure up here with some argon, nitrogen, and hydrogen gases. You don't need to actually copy this down, but I just wanted to give you a visual for this. So these 3 samples of gases are all at the same pressure, which is actually standard pressure, 1 atmosphere. They're at standard temperature, which is 0 degrees Celsius. Each of these have different masses, however. If you look up the mass of argon, so argon gas, 1 mole of this on the periodic table, is about 40 grams. If we look up nitrogen gas, it's 14 times 2, it's about 28 grams. And hydrogen gas is very small particles, and H2 actually gives us a mass of only 2 grams. However, in every single one of these containers, we have the same number of molecules. Those are all representing 1 mole. So what's kind of strange about this, you're saying, okay, we've got the same conditions, same number of particles, but even though those particles are totally different sizes, they're occupying the same amount of space. So what this tells us is if we have, if we have pressure, temperature, and the number of molecules, okay, or the number of moles, all the same, the amount of space that those samples will take up, or the volume those samples will occupy, will be the same, even though mass and individual particle size is different. So it's kind of like I'm telling you that if we actually had, I had a visual for this, sorry, there we go. If I had a bunch of tiny particles, a bunch of big particles, the individual particle size doesn't matter. They're stored under the same conditions. They're going to take up the same amount of space. This was actually a hypothesis by a guy named Amedeo Avogadro. And we do sing a little song with this in class, so you have to make sure that you get that song because it really helps you to remember this. So Avogadro's hypothesis says equal volumes of gases at the same temperature and pressure, so equal volumes, same temp and pressure, will have the same number of molecules. So no matter what gas we're talking about, if they're stored under the same conditions and we have the same temperature, pressure, and the same amount of volume, we're going to have the same number of molecules. So it seems a little bit crazy. So 40 grams of argon, 28 grams of nitrogen, 2 grams of hydrogen are all actually taking up the same amount of space. That's sort of weird. What actually happens is, even though these particles are very different sizes, the overall volume of the sample can be the same because they're so far apart that individual particle size sort of doesn't matter. So these tiny little nitrogen molecules over here on the left-hand side just have more space between them than the larger argon molecules, or atoms, I should say. So there are some calculations we need to do with these. We tend to do these right at STP, and at STP, 1 mole of any gas occupies 22.4 liters. So if I told you you had 44.8 liters of a gas, it'd be pretty easy to know that that's 2 moles of a gas at STP. So we can solve these the way that we've been solving a lot of our other problems. If we have a sample of gas at STP, which means we're able to use our 12.4 conversion factor, or 22.4 conversion factor. So we could use 1 mole of gas over 22.4 liters, or 22.4 liters over 1 mole of gas, depending on what we need for the problem. So we are given liters. We want to know how many moles are in that sample. So we're starting with our 12.5 liters. We want to end up in moles. We need liters to cancel out. So I'm going to choose this first conversion factor right here, which puts my liters on the bottom for me. So this is 1 mole over 22.4 liters. Liters are gone. So I'm just doing 12.5 divided by 22.4. So you should get 0.558 moles. We have 3 significant figures. The 22.4 does limit us to 3, and also 12.5 has 3 significant figures as well. So we can also say if we have 1 mole of gas, we know it's going to occupy 22.4 liters. A half a mole of gas is going to occupy 11.2 liters. We can use our same conversion factors here we did on the last one. In this problem, we're just starting with a different amount. So we want to actually find out how many liters are in 2.5 moles of oxygen. So my starting amount is my 2.5 moles. I want moles on the bottom. I'm going to put 1 mole down here and 22.4 liters up here. Moles are going away. I'm actually multiplying here. So you're going to do 2.5 times 22.4, which gives you 56 liters. Which you only have 2 sig figs there because of that 2.5. Now, we can actually do a much more complicated problem. So in this particular problem, they're giving us our 4.0 liters of gas at STP, and we want to know how much, what the mass of that would be coming out in grams. So we're actually going to start with our 4.0 liters over here. And remember, our ending amount over here we want to come out in grams, so we got to keep that in mind. So the first thing I need to do is I need to get rid of liters. So I'm going to put liters on the bottom, and that equates to a mole. Liters will go away. Now I have moles. I want my answer to come out in grams. So I want my 1 mole on the bottom, and I'm actually going to use here my GFM. Now the gas that I'm talking about is oxygen gas. Remember, that's O2. So you're going to do 2 times oxygen's mass on the periodic table, which is going to give you 31.9988 grams. Moles are going to cancel. So you'll do 4 times 31.9988 and divide that by 22.4, and you should get 5.7 grams. Since 4.0 is 2 sig figs, that's how many sig figs we're limited to. So in our next problem, we have a sample of 66 grams of carbon. So they're starting us with 66 grams of carbon dioxide, and we want to know how many liters that is going to occupy when it's held at STP. So now we have to start with our 66 grams over here. And remember, we actually want to end up in liters. So we're not going to use our liter conversion quite yet, because first we want to go to moles. So you're going to look up CO2, add your masses, get your GFM. So the first conversion factor I'm using right here is actually my GFM conversion factor. And I do need grams on the bottom. So I'm going to put my 44.0098 for my GFM calculation, grams on the bottom, and my 1 mole on top. That will allow me to cancel out my grams. My next factor is where I'm going to actually be able to take moles into liters, which is what I want to end up with. So I'm going to put 1 mole on the bottom and 22.4 liters on top. My moles will cancel out. So you're going to do 66 times 22.4 and divide that by 44.0098. And you should get 33.6 liters, 3 sig figs in that. So please pause the video, take a minute, and calculate the answers to the next 2. Number 1, you should have gotten 38.9 grams, shown the work for you right there. And number 2, grams cancel, moles cancel, and when you do your math for this one, you should get 33.6 liters. And that is all for liter and mole conversions.